Okay, thank you everyone for coming back in time. We are going to start the first talk of the conference, the actual conference. And our first speaker is Stephen Jordan from Google, who will tell us about their new work on optimization by decoded quantum interferometry. Stephen, please.
Thank you. So this is joint work with Noah Shutty, Mary Wootters, Adam Zalcman, Sasha Schmidhuber, Robbie King, Sergei Isakov, and Ryan Babbush. And we have a preprint about this on the archive since August. And also we have a version 2 that's going to come out tomorrow with a few more results. So the question that kind of motivates this research is whether quantum computers can achieve exponential speedup for optimization. And I think it's fair to say that this has been a major question in the quantum algorithms community from the very beginning. And one thing that's tempting about it is that optimization problems do have generally the right characteristics for the possibility of an exponential quantum speedup. That these are sort of big compute, small data problems, or to put it more precisely, for a lot of these problems, the computational time classically to solve them scales exponentially as a function of the number of bits needed to specify the problem. And that's really a prerequisite for the possibility of having a exponential speedup. And now one thing to keep in mind is that many optimization problems are NP hard. So one doesn't expect exact solutions in polynomial time classically or even quantumly. And but there's a different question you can ask besides can we find the exact optimum for every instance. You can ask about finding approximate solutions. And so that's sort of quantified by how good the approximation is. And perhaps there could be some region where you can find a level of approximation on a quantum computer in polynomial time that would require exponential time to find classically, where the highest approximation you can get classically is something lower in polynomial time. And many interesting approaches to getting quantum speedups for optimization problems have been proposed over the years, such as adiabatic computing and QAOA. But I think it's fair to say that modulo some isolated caveats, this remains essentially an open question. And so our approach is based on a physical intuition. I think it's often helpful to have a point of contact between physical intuitions and algorithms research. And many of the previous approaches have used Hamiltonians as the natural point of contact between optimization and quantum physics. And this allows us to draw upon ideas having to do with tunneling and so on. However, DQI starts with a different premise. What we observe is that objective functions of many of the important and commonly studied optimization problems have Fourier transforms that are very sparse. So if you take the Fourier transform of the objective function, you'll see that in principle, if it's some function on n variables, there could be exponentially many non-zero amplitudes in the Fourier transform. But in fact, the number of non-zero amplitudes is only polynomial. And furthermore, oftentimes, those non-zero amplitudes are on wave vectors that are themselves structured in some way, such as being sparse. And so we try to use that as our initial point that we exploit in our algorithms. And so the physical intuition is that in DQI, we use a quantum Fourier transform to obtain constructive interference on symbol strings that have a large value of the objective function and destructive interference on symbol strings that have a small value of the objective. So to describe the algorithm, I'll have to give a little bit of background on lattices and codes, but I'll try to keep this just to the bare minimum that we need to understand the topics at hand. And so what is a lattice? A lattice is some set of vectors that's closed under addition and subtraction. So here's an illustration of one. And we can also consider the more general case where instead of operating over ordinary numbers, we operate over a finite field. And it's exactly the same idea, really, but we just don't call it a lattice anymore. We call it a linear code. And so here's an example of that. This matrix B is the generator matrix of the code, and then its image is the code itself. So there are some basically one key computational problem that's at the center of lattice encoding theory, which is given some point in space V, which I've drawn with this little red dot, we want to find the nearest vector in the code C. And for the purposes of this talk, our metric of distance will be Hamming distance. And we can think of this as a decoding problem because your displacement from this nearest code word is the error that you're trying to correct. And in general, this is an NP-hard problem. But there are two different ways you can sort of modify this problem to make it easier. So the first one is you can ask, instead of for the nearest code word, an approximate nearest code word. And so here, as you can see, illustrated with the red dot, there's one code word that's very near, but maybe you find one that's still pretty close, but not actually the nearest. And so you can kind of tune the difficulty of this problem based on how good of an approximation you demand. So if you say, well, we need to find something that's at most twice as far away as the nearest code word, then that's still pretty hard. But if you say, well, if we only demand that it's at most square root of n times as far away as the nearest one, then it becomes an easier problem. And so by changing this approximation factor, you can tune this problem between being NP-hard, easy, or in between. A different way that you can kind of ease the problem of nearest code word is, instead of an approximation problem, you turn it into a promise problem. So now you still demand finding the nearest code word, but you restrict the problem instances. You say, the person generating the instances has to promise that the points in space that they're going to give you, these vectors v with the little red dots, are promised to be quite close to the code. So again, this is something where when you tune that radius of your promise, this tunes the difficulty of the problem. If that radius is very small, you can always just do exhaustive search around the given point and even find nearest code word. If the radius becomes sufficiently large, then of course these green circles will expand and eventually fill up the whole space, and you get back your original unrestricted problem, which is NP-hard. And as you change the radius, you can smoothly change the difficulty of the problem. And this is called bounded distance decoding. So the last thing I will say about codes is the notion of a dual. And this is the set of code words that are orthogonal to the ones in the original code. And it turns out that a code and its dual are related by a Fourier transform in the following sense, that if you have a sum of delta functions that are right at all the code words, and you take the Fourier transform of that distribution, you'll get a sum of delta functions that are at all the points of the dual code. And so you can just flip back and forth between the code and its dual by a Fourier transform. And a more algebraic way of flipping back and forth is that you can go between a code and its dual by interchanging the roles of the generator matrix and the parity check matrix. So what that means is the code, if you have some matrix B, which is sort of the basis vectors of the code, then the code is the image of B, and the dual code is the kernel of B transpose. So there's actually a long history of work relating to quantum computing and lattices and codes. And I'll sort of give you an overview of DQI that kind of ties it into this history and also explains DQI from a point of view that's very geometric. And in fact, there's two different ways of thinking about our new algorithm DQI. One is this kind of geometric one that I'll focus on in these slides. The other one is a more algebraic point of view that we use in our paper. And so if you want to see the algebraic view, look in our paper, but I felt that a geometric point of view would be more suitable for slide format. So this might give you some intuition, but I think if you want to work on the subject, you probably want to also look at the algebraic case. So anyway, there was some insights that came in the early 2000s from Aharonov, Tashma, and Regev, which showed that you could have quantum reductions between various lattice problems using quantum Fourier transforms. And there are many such reductions, but the one I'll focus on is illustrated here. These are images pasted straight from one of Regev's papers, which sort of generalizes this fact I gave you on the previous slide, that if you have a superposition over delta functions, its Fourier transform is delta functions on the dual. Now suppose instead of delta functions at each code word or lattice point, you have peaks of some given shape. If you take the Fourier transform of that, what you get by the Fourier convolution theorem is a superposition over delta functions on the code that's dual to that one, but with an envelope function whose shape is the Fourier transform of the peak shape that you started with. And so basically, by standard Fourier analysis, what you know is that if the width of these peaks is radius r, then correspondingly, the width of this envelope function on the other side is going to be of order 1 over r. And so that's just a math fact which gave some reductions back in the early 2000s, but did not give, at that time, quantum algorithms. And it's in more recent work from the 2020s, within the past 5 years, actually, that there's been kind of a renaissance of this type of thinking that's yielded a lot of very exciting, I think, results of a more algorithmic nature from Gendry and collaborators and Tillich and collaborators. And this DQI work could be seen as another example of that. So how can you use this for a computational reduction? Well, one quantum algorithm you could imagine is, well, let's just try to make this superposition of peaks shown on the right. And how can we make it? Well, it turns out that if you can do the bounded distance decoding problem by some classical or quantum algorithm, then you can make this superposition with peaks whose support is out to radius r, where r is the radius to which you can do bounded distance decoding. So then once you've done that, you can take a Fourier transform. You can get this weighted superposition with an envelope function over the dual code that's shown on the left. And then you could just measure it in the computational basis. And then you would get a biased sample from these dual code word or dual lattice elements, which is biased towards the short ones. And that's actually solving a hard computational problem if the bias is strong enough. Finding short lattice vectors is hard. And so in complexity theoretic language, we'd say, well, there's a quantum reduction from finding short vectors to solving bounded distance decoding. And if we can, and sort of the quantitative version is, if we can solve bounded distance decoding out to radius r, we can make peaks out to radius r, which means that we get this bias giving us short code words with length on the order of 1 over r. And so the question then becomes, does this reduction give you anything? Because on both sides of this reduction, we have problems that are NP hard in the worst case. And it's only once we fiddle around with this parameter r that we start to say, oh, well, maybe if we make r small enough, then the bounded distance decoding problem becomes easy enough to do. And then that implies how short of vectors we get on the other side, 1 over r, and is that something interesting and hard? Well, it turns out that if you just look at general lattices, this doesn't really help you do anything that you couldn't do classically. It gives you a lot of very interesting reductions between problems that help set the foundations for post-quantum cryptography, but it didn't give us algorithmic quantum speedups back in the early 2000s. One of the new key ingredients from the recent work within the last 5 years, and in particular our work on DQI, is that instead of considering sort of general lattices and codes, we consider ones with more structure. And the idea is, can we find some structure in these codes that helps a lot more with the bounded distance decoding problem than it does with the sort of finding short code words or near code words problem that's dual to it. And so this was done in some work by Chen-Lu and Jandry and Yamakawa and Jandry, not exactly for optimization problems, but for search problems of finding things that satisfy all the listed constraints. It's done by us in DQI. And actually, already very quickly after our work, there was some follow-up work by Shayu and Tillich, which used some fancier decoding to improve our parameters of our algorithm. So now let me get into the specific content of our paper, the decoded quantum interferometry algorithm. So we consider the case of lattices over finite fields. The simplest thing that you can keep in mind is the integers mod p, where p is a prime. And so these are called linear codes. And instead of optimizing for short vectors, as I showed in the prior slide, we're going to optimize for more general objectives. Essentially, this can be applied to any objective function whose Fourier transform is sparse. And that includes really a large fraction of the commonly studied combinatorial optimization problems. And the two forms of structure that we consider in the code to see whether they change the difficulty on one side of the duality more than on the other, and thereby allow us to have quantum advantage, are, first of all, sparsity, so that this generator matrix for the code would be sparse, which corresponds to constraint satisfaction problems where each constraint involves a limited number of variables, such as max k sat, max k XOR sat, and so on, constant k. And the other one is where we have algebraic structure. And this is actually, just to skip to the punchline a little bit, it's in the algebraic structure case that we believe we have found an example where we can achieve a certain approximation in polynomial time quantumly that we are aware of no polynomial time classical algorithm. Now, before getting into more of that, I'll just devote one slide to sort of relate this to what you'll find in our paper if you decide to read it. So there we take a more algebraic approach, which helps us with calculating in detail how the algorithm behaves, and also gives a little bit different conceptual insight into it. We start by having some cost function, f of x. X you could think of as being a vector of bits, for example, if we're working mod 2. And then given any polynomial of degree L, what the DQI algorithm prepares is a state where the amplitude on a given bit string is p of f of x. So where f of x is the objective. So you can see that if p is a high degree polynomial, you can create a very strong bias toward bit strings that have a large value of the objective. So for example, we could just choose p of f to be f to the L. And now when we measure, we would have a probability of getting a given bit string, which is f to the 2L. And so that's a very strong bias if L is large, which pushes you towards large value of f. Now, we can't always do this. The case that we can do this efficiently is when this code cperp can be decoded out to L errors. And what is cperp? Cperp is the code whose parity check matrix is basically just the matrix that whose rows contain all of the wave vectors that have non-zero amplitude in the Fourier transform of f. So what's an example of how we can apply this? So one problem we can apply this to, which is probably the simplest case, is max XOR sat. And here we're given some m by n matrix, mod 2, where m is greater than n. And we're given some vector with m values in it. And if we say that b sub I is the ith row of the matrix capital B, then we have this list of linear equations mod 2, which are bi dot x equals vi. And these are the constraints of our objective function. So in other words, we could write that as we have this matrix equation bx equals v. And as I said, m is greater than n, so this is an over-determined linear algebra problem. We can't satisfy all the constraints, So we want to satisfy as many as possible. That's what makes it hard. And so it turns out that if you just make a objective which counts how many of those constraints you've satisfied, the non-zero amplitudes of the Fourier transform of that are on the wave vectors, which are exactly these same vectors b sub 1 through b sub m, the rows of this matrix B. And so this makes it something that DQI can be applied to. And you can also view this as a nearest code word problem if you think of C as being the code generated by, with the generator matrix B, then the max XOR set problem is exactly the same as finding the code word in C with the smallest Hamming distance from the given vector V. So it's just another way of looking at it. You can think of it as a code problem, or you can think of it as a classic optimization problem. And so DQI uses a Fourier transform, in this case specifically a Hadamard transform, to reduce the approximate nearest code word problem on this code C to the bounded distance decoding problem on the dual code C perp. So that's exactly this kind of same picture I showed with the envelope function and the little peaks on the two sides of this Fourier duality. And so then these problems that we're reducing from and to are both NP hard problems in the worst case. And so the question we have to ask is, well, does this really help us with anything? We've just reduced one hard problem to another. It seems like maybe we've gotten nowhere. But really the question is a quantitative one, because there's, on one side, we have an approximation factor, and on one side we have a bounded distance promise. And how those quantities relate tell us whether we've gained anything or not. And so we start with a problem of finding a code word in some code C that matches S bits of an arbitrary target string, which I called V. And this gets reduced to, by our quantum reduction, a different problem, which is given a string within radius L of C perp, find the nearest code word. So these are NP hard if S is sufficiently big or L is sufficiently big. But we can ask, for a given L, what is the largest achievable S via DQI? And so how do these two parameters relate by the Fourier transform? And the second question is, what structure in the code C allows the code C perp to be decoded efficiently out to large L? So the first question is sort of the easier of the two. It's really a Fourier analysis question. It's not so easy, but we do have basically a complete solution to it. And so here's the equation that just tells us the answer. So L is this number of errors we can correct, M is the number of constraints, S is the number of constraints that we satisfy, that are satisfied by the bit string we measure at the end of our algorithm. And so the expected value of S divided by M, in other words, the expected fraction of constraints satisfied, is given by this formula, a half plus square root of, et cetera. And so this equation, we call it the semicircle law. And it just fully answers question number 1 from the previous slide. But that still leaves us with the second question, which is, what specific structure in the original problem is something that's going to help us solve the bounded distance decoding problem on the dual more than it helps us solve the original problem, such that this quantum reduction gives you an advantage. So we'll address this question by looking at 2 examples. Before that, let me show you, here's a plot. This is showing the semicircle law. The reason I show this is not just to remind you what a semicircle looks like. The other point really is that the semicircle law is really asymptotic. That's in the limit of large M. But actually, we can also compute exactly what happens for finite M. It's just instead of a formula, it becomes an eigenvalue problem for a matrix of polynomial dimension. So you can always, if you need the quantitative details, you can get them efficiently. OK, so the first kind of structure we considered for question number 2 of how to structure help was sparsity, because this just is all over the place in combinatorial optimization, and so it's a natural thing to consider. And so we have this list of constraints, And suppose we have the promise that each variable is contained in at most d constraints. So this means that correspondingly, if we write things in matrix form, this matrix B is d sparse. And so what does that tell us? So in this case, C is a low-density generator matrix code. These are actually not used very much. They're not good codes for communication, but they have a name. And DQI takes this approximate nearest code word problem, or max source set problem, you could also call it, for these low-density generator matrix code, which corresponds to bounded degree max source set, and reduces it to decoding of a low-density parity check matrix code. Now, low-density parity check matrix codes are very good codes, and they have very good classical decoders that can decode efficiently out to many errors. So this was a source of optimism for us, because if we can decode more errors, this quantity L is larger, the degree of our polynomial that we can bias by is larger, we get better results as dictated by the semicircle law. We're out on the, we're out on the right-hand side of this curve, the good part, when L is large. So what does this mean? Well, this means we can actually do kind of experimental research on quantum algorithms, even with tens of thousands of variables, no problem. Because what we can do is we can choose some ensemble of instances of max XOR set. We can then write down the corresponding LDPC code that's dual to that. We can just test experimentally on our ordinary computers how many errors can we correct efficiently on those LDPC codes. Via the semicircle law that tells us what the performance of the DQI approach will be. We can also test classical optimizers on the original problem, and then we compare. Who wins? Is it DQI or is it the classical optimizer? And if classical wins, we go back to the beginning and try again with a different ensemble, a different choice of decoder, and so on. If quantum wins, well, it's game over. We just have party time. So that's what we spent actually months on. And it turns out that those classical optimizers really are quite formidable for these sparse problems. It's tough to find an advantage here. Sparsity helps on both sides of this duality. And it's very tricky to see if you can thread the needle and find some specific pattern of sparsity that helps a little bit more on the dual than it helps on the original. The best we have found so far is an example where we very finely tuned the sparsity pattern to try to optimize it to be as advantageous as possible for the decoder that we used, which was belief propagation, and as disadvantageous as possible for our main adversary, which was simulated annealing. And we were eventually able to construct an example where DQI would get a better approximation than we were able to obtain directly with simulated annealing, even if we pushed it very hard for many iterations and tweaked the parameters and so on. We do not put this forth as an example of quantum speedup because although we were able to beat simulated annealing, we were also able to find a customized classical heuristic that's kind of specific to that problem, which came out on top ultimately. But my takeaway from this, so now we're moving away from objective statements to sort of like interpretations, but in my opinion, I would take this as somewhat encouraging in the sense that already using kind of standard off-the-shelf decoders, namely belief propagation, which is kind of the standard workhorse of LDPC decoding, we were at least able to find one example where we beat actually not only simulated annealing, but all the general purpose classical optimization heuristics that we tried. So it suggests to me like maybe if we push harder with more specialized decoders, which are a little bit more tailored to the problem at hand, maybe we could actually get an outright win. But that's speculation. Or one could also consider quantum decoders, which I'll comment on briefly in the open questions section. But now let me move on to our other example, which is really the one that's our success story. And so that's around algebraic structure. So the problem that we considered, we refer to as optimal polynomial intersection. And it's kind of a, I think of it as being a polynomial regression problem, essentially, kind of generalized polynomial regression. And the statement is we're given m targets, and we want to intersect as many as possible with a degree n polynomial, where the degree of polynomial is less than the number of targets we're trying to hit. And so that's why it's kind of an over-constrained problem. And everything is mod p here. So the polynomials are working over the finite field, which is the integers mod p. And so here's an illustration of that, which shows what I mean by targets. So the first thing you could say is, well, in a standard regression problem, the targets are really just points. You're trying to fit these points. But more generally, you could say, well, maybe we don't have to fit it exactly. Maybe we have little intervals we're trying to get within some certain distance of these points. But even the most general thing is, well, these targets could be arbitrary subsets of the finite field. And that's the general case that we consider. And so here, these arbitrary subsets are illustrated in this kind of yellowish color. And these two, the red and the blue curve, are examples of two different polynomials which both achieve the same value of the objective function because they both intersect the same number of these subsets. And this is a very hard optimization problem classically for a few reasons. One is that the objective landscape is very rough, so any kind of simple hill climbing heuristics get stuck quite quickly. One way to see that is you can see that these two polynomials are very different from each other, but achieve the same value of the objective in this illustration. And the other issue is that it's a very dense problem. So you have your list of constraints. Does the polynomial intersect this subset or not? And then the next subset and the next subset. Well, it turns out that you can kind of see, actually, that each constraint involves every variable in your problem. The free variables in your problem that you're trying to optimize are the coefficients in the polynomial, and all of those determine the value of the polynomial at a given input, at a given argument. And when you have this density property, all of the standard heuristics, like simulated annealing and all the things that are related to that, they fail very badly. Those heuristics are good when each constraint involves a small number of variables. There's actually a more precise thing you can say, which is that if you flip one symbol in your optimization, then essentially you're kind of re-randomizing your value of the cost function because you've perturbed every single constraint. And so it's almost as though simulated annealing, flipping one bit, is equivalent to just jumping to a random point, which means that things like simulated annealing should be expected to behave basically the same as random uniform search. And indeed, empirically, you can see that that's essentially true. So this is a very hard problem for heuristics. It has been studied before in several different classical literatures, which all give it a different name. And oftentimes, they're considering various special cases. So we gave our own name, optimal polynomial intersection, to this problem, which tries to encapsulate all those different special cases. But it's been studied in the crypto literature as well as in the error-correcting coding theory literature and a few other places. And some classical algorithms have been devised for it. But anyway, what our observation is that if we start with this problem and we do our business with Fourier transforms and we say, well, what's the decoding problem that's dual to this, it ends up being recognizable as the decoding problem for a Reed-Solomon code. And this is very good news for us because if you know coding theory, you know that Reed-Solomon codes are basically like the best codes ever. They're sort of like the Platonic ideal of everything you want an error-correcting code to be. They have great distance. They have great decoders. We know everything about them. They're very elegant. There's only one thing that people don't like about them from a communications point of view in practice for transmitting messages, which is that they're not over a binary alphabet. They're over this kind of mod P alphabet. But we're not in a communication context. We're talking about algorithms, so we don't mind at all. That's no problem for us. And so we can just take one of these algorithms. That's a polynomial time classical algorithm, which decodes provably guaranteed with 100% success probability out to half the distance of the code. And it's very efficient. So the one we look at is Berlekamp-Massey algorithm. But there are other ones you could choose. Doesn't matter too much. We plug that in as the decoder in DQI. We use our semicircle law. And what do we get? So, well, what we get depends on the parameters that we choose. So as our primary example, we looked at the case where the problem is over-constrained by a factor of 10. So we take the number of constraints to be 10 times the number of adjustable parameters, which in turn is equal to the degree of the polynomial. And we take these subsets that we're trying to hit to be actually quite large. So we take them to be half the size of the finite field that we're operating over. And that's sort of analogous to the max XOR case, because each constraint has, if you were to toss your variables at random, would have a 50% chance of being satisfied. So this is a rather different regime than has usually been studied, and that, well, it's a different regime than the ones for which we already have good classical algorithms. In the coding theory literature, you would usually look at ratios m over n that are smaller, because those correspond to higher rate codes. And it would be somewhat rare to consider subset sizes as large as r over p equals a half. In fact, in the crypto literature, they often consider r over p to be exponentially small. And so because we're in this different parameter regime, those algorithms really just totally break down and do not work well on this problem. We kind of scoured the literature, went through, and none of the algorithms that we found in the literature really worked in this parameter regime, which is natural in our context, but not so natural in the prior ones that people have considered. And so these algebraic algorithms all broke down, so that just leaves the classical heuristics like simulated annealing and so on. And as I mentioned, those also fail quite spectacularly and essentially scarcely outperform just pure random search. So what is our result that we can state, which is that in this case, the matrix B that sort of quantifies the decoding problem, it turns out to be recognizable as the parity check matrix of a Reed-Solomon code. So that's a very structured matrix. Entry Bij of the matrix is just gamma to the I times j, where gamma is a element of the finite field that can generate the whole field by multiplication. And this can be efficiently decoded out to L equals n plus 1 over 2 using Berlekamp-Massey. We plug that into our semicircle law. At m equals 10n, we find that DQI achieves a satisfaction fraction of about 0.72. Simulated annealing and things like that converge to half, which is what you get from random search in the limit of large problem size. There's something we consider which is called, we call the truncation heuristic. In some contexts, people call it Pronge's algorithm. But all it really is because this is an over-constrained problem, you can just throw away extra constraints at random until it becomes sort of a square matrix type problem. Use Gaussian elimination, and then of all the constraints you threw away, well, about half of them, by random luck, you'll still satisfied. And so when m equals 10n, what you get is 0.55. And that's actually, among polynomial time classical algorithms that we know, That's the best we've got for this problem. And so there's a huge gap between this 0.55 and this 0.72. And so as far as we know, once you get past 0.55, all you have to fall back on are exponential time classical algorithms, which are essentially brute search or slight refinements of brute search, such as using birthday paradoxes and things like that. And so this is, in a sense, the main result as far as speedups in our paper. But of course, one reason for giving talks like this is to sort of provoke any classical computer scientists in the audience to give a very hard look at this OPI problem. Although in the literature, we search pretty carefully, and we're pretty confident that there aren't algorithms already there that attack this. Maybe someone clever could come up with something. You know, that's always the game with quantum algorithms. It's, technically speaking, it's even true for factoring. Maybe someone will find a polynomial time factoring algorithm classically. But of course, this problem has not attracted as much scrutiny as factoring, and we hope to attract some more. So, in a way, the most important slide, I think, of this talk is about open questions. So, as I mentioned, one of these questions is, can anyone find a polynomial time classical algorithm that matches the performance of DQI or exceeds it on this OPI problem? So I've already sort of laid down the gauntlet. It's been out there for 6 months. So far, no one's come out of the woodwork, but that's not such a long time in the scheme of things. So I propose that all to you. So the next major open question that I've already alluded to is whether DQI can achieve quantum speedup on algebraically unstructured problems, these ones that maybe the only structure to exploit is sparsity. And there's several approaches that one could take toward this. One is you could just try to devise new classical algorithms for decoding that are a little bit more tailored toward the problems that arise in DQI. And in particular, if you take these optimization problems like max K XOR set and you make them a little bit less sparse, this quite rapidly degrades the performance of simulated annealing. We have kind of a heuristic argument that says that if each variable is contained in D constraints, then what simulated annealing should be able to find in polynomial time, the satisfaction fraction it achieves in polynomial times goes like a half plus constant over square root D. And we don't have a proof of this, but we have a heuristic argument, and it matches quite well to what we see in computer experiments. And so what you really want to do is you want to push towards slightly denser problems, which degrades the performance of simulated annealing that we're competing against, but it does not degrade at all the distance of the code and the information theoretic capacity of the code on the other side, which determines the maximum possible value of L that we can achieve, and therefore the maximum possible performance of DQI. The problem is, what we really care about is the efficient decodability on the other side. And as we make the parity check matrix denser, then the known efficient algorithms like belief propagation start to perform worse in practice. And so there's the question of, well, could you consider other decoders that do better than that in terms of their tolerance of density? And I think it really hasn't been studied that much, because in a communication context, why would you make your life harder artificially by choosing a denser parity check matrix? So that's one direction you can go. And there is some literature on this, particularly regarding linear program-based decoders and neural network-based decoders. A different thing that could be considered is also quantum decoders. So it turns out that the decoding problem that we reduced to, I've described it as classical error correction, But fundamentally, the errors are in superposition. It's not a probabilistic mixture of errors. It's a superposition of errors that's coherent. And information theoretically, that's advantageous, actually, basically because the Halevo bound is more advantageous than the Shannon bound. But then the question is, can you actually design efficient quantum circuits that exploit this advantage? And there is some literature on that. It's a very nice algorithm from Joe Rennes called BPQM. There's a method from Chen, Liu, and Jandry called filtering. There are all kinds of interesting things that you could try to use there, as well as an interesting technique using USD measurements by Tillich and collaborators. So that's a second direction that I would like to invite people to think about. Another one is what other algebraic problems might be attacked with DQI. So there's kind of an interesting history here, which is that our discovery of this advantage, what we think is an advantage, for the OPI problem, we arrived at it backwards. We did not start by thinking, well, here's the OPI problem, let's try to attack it. We started by saying, like, well, let's consider the decoding problem of Reed-Solomon codes. We know that this is going to be very favorable for DQI. And, well, by the Fourier transform, there's some optimization problem that's dual to that. And we didn't really know at first whether that was an interesting or natural or hard optimization problem. And it's only by sort of squinting at it the right way we could see that it could be interpreted as a polynomial regression problem, and was actually quite natural and even studied before in quite a few classical algorithms papers. So you could just try to repeat that history. Well, what if we plug in other types of algebraic codes? There are many very nice algebraic codes known which have very good decoders. Plug them in and try to see whether the Fourier dual optimization problem is something natural or is it just something that's very contrived. And actually, although I state this as an open problem, we do have some progress on this, which you will see in our version 2 on the archive, which I believe comes out tomorrow, which is that we can generalize from Reed-Solomon codes to Reed-Muller codes, and the dual problem turns out to be multivariate polynomial regression. And so probably there's actually a region in parameter space where this speedup extends into the multivariate direction. We've not yet done a thorough job of comparing against classical algorithms. And another kind of more theoretical question you could ask is, can OPI be reduced to the abelian hidden subgroup problem? I think this is kind of an interesting question. As far as we know, this is doing something different from Shor's algorithm and so on. All these old algorithms that are based on sort of period finding. This, although it does use Fourier transforms, it's using them in a very different way. And so a formal, sort of semi-formal way you could state this question is, well, if you were just granted the ability to solve a abelian hidden subgroup problem efficiently, but no other power than that, you just had classical computing plus abelian hidden subgroup, could you solve the OPI problem as well as DQI does? And we don't know. So my conjecture is the answer is no, but my collaborator, Mary Wootters, her conjecture is that the answer might be yes. So this is a really very open question. Now, one question I often get asked is whether DQI breaks any crypto systems that were thought to be secure against quantum computers. And we have worked on this. So far, we haven't found anything, but it's not completely implausible, I think. But it's an open question. And lastly, you could look beyond optimization entirely, even beyond lattice problems and optimization entirely, because as I stated in the slide with the algebraic point of view, fundamentally what we're doing is if we have a function f that has a sparse Fourier transform, what we can put into our amplitudes is p of f, where p is some polynomial whose degree is limited by our ability to decode some dual problem. And you could think, and so all we do with that state is measure it, which is sort of like the weakest and most obvious thing to do with it. But once you can make states like that, you can consider different things. You could take pairs of states, compare them to each other to see if they have large overlap or not. You could use them as the starting point in other algorithms for counting problems or for simulation problems. And so you could try to think outside the box beyond optimization with other applications. So I've really spent a disproportionate amount of time on this open question slide. That's by design. I'm hoping that people will take inspiration and do things with these tools that we didn't anticipate. So thank you for your attention.
Thank you for the excellent talk and perfect timing. Are there any questions for Stefan? Microphone. I'm going to start here. Please wait for the microphone because this is recorded. And
first off, thank you for the excellent talk. I'm curious for, very popular major combinatorial problems such as traveling salesman, packing problems, so on and so forth. Has anybody demonstrated that even, maybe in special cases of those problems, they admit the structure such that your algorithm would be beneficial? Thank you. Also, I'm curious as well, do you think some of these ideas could be eventually extended to nonlinear programming as well?
Yes, good question. So specifically about traveling salesman problem, I'm not very optimistic. So traveling salesman, you can sort of re-express as even as a max XOR set problem, which is sort of the most native form for DQI. But I think the overhead you get from that is going to undo kind of any potential advantage. And furthermore, the classical approximation methods are remarkably good for that. I think if you are looking at algebraically unstructured problems and you're hoping for speedups there, I think the best targets are sort of the classic ones phrased in terms of constraints involving modest number of variables, things like max sat, max XOR set, and so on. These are sort of the nicest target. And then if you ask, like, okay, what if we want something that's a little more applied, a little more industrial? What are the problems that you see in the real world that look closest to that? And so I'm not an expert on real-world optimization problems, but I did have some, in a prior role, I did have some contact with that industry. And a lot of the most practical things that look closest to max XOR set are kind of placement problems. Things like, where would you put cell phone towers to achieve coverage using as few towers as you can? Or where would you put sensors on a network of pipes so that you can get coverage? These things where you're basically minimum vertex cover on graphs, minimum set cover, these kind of problems, those I've seen arise in the real world, and those look actually close to these max XOR set and QUBO type problems that we theorists like to study.
I think I just have a question about the crypto side of this. The closest I could think of is basically elliptic curve cryptography, where we try to do some kind of elliptic curves over finite fields. Normally, you try to multiply multiple primes so that you make the elliptic curve group is bigger. And after that, then you do the analysis. It's not linear because you have y square equals some polynomial over finite field. Have you looked into that kind of area?
No, we haven't looked into elliptic curve stuff because I feel that kind of Shor's algorithm for a discrete log kind of has it covered already. The thing that we have thought about a bit are lattice problems like learning with errors, learning parity with noise. And I would say for the general version of those problems, at this point, based on our preliminary results, it does not look very likely that DQI breaks them, at least using the techniques that we've tried so far. I think you would have to use fancy quantum decoders to have any hope. But then also, if those problems have algebraic structure, if they're ideal lattices, people like these kinds of algebraic structure because it reduces your key sizes. But then it induces some kind of algebraic structure on the dual decoding problem, and the question is, can you exploit that And, well, we don't really know the answer.
Other question in the back?
Okay, thank you. I like to ask a question about the quantum computational advantage or quantum supremacy. You claim that you have an exponential advantage merely from numerical experiments that its satisfiable rate is larger than the formal methods. However, for example, in Boston sampling, they claim that there is a quantum advantage from a complex series perspective. They assume that if there is any classical algorithm that can sample or simulate the distribution result of that algorithm, then maybe some maybe polynomial hierarchy will collapse to a certain level, and that's a violation. But in your work, you only claim that from a numerical perspective. So I wonder if this might be a little too strong, this claimant. Okay, thank you.
Sure, yeah, it's a different kind of claim than the quantum supremacy claims. It's more like it's analogous to the claim that Shor's algorithm achieves super polynomial advantage. It's really just we compare against algorithms that we know about. And it's not even really at the same level of that because, of course, the problem that we're solving isn't studied as heavily. And so, maybe I should call it a conjecture instead of a claim, just to be careful. But you do raise some questions. So one of them is, could we use DQI to sample from probability distributions that you can provably not sample from classically without collapsing the polynomial hierarchy? I think that's an interesting question. We don't know the answer to that. And another one is, suppose we wanted to find out what are the concrete resource requirements to achieve advantage in the sense of, let's try to solve an OPI instance that's out of reach for classical supercomputers. What's the size of that instance? And therefore, what are the requirements in terms of qubits and quantum gates, particularly non-Clifford gates? And that's something that we are now thinking about. And this is not a NISQ-friendly algorithm. It needs fault tolerance. But it's not that horrible. Like, it might be the case, we're still investigating this, but it might be the case that the crossover point is at its slightly smaller resource requirements than the crossover point for factoring. So if that's true, it would be interesting. We're not claiming that yet, but it's at least plausible based on our preliminary investigations.
Okay, we are told that we need to stop now, and this tank is tripping again.